Welcome to the answer video of the fire hose exercise. The problem introduced involves a horizontal tube which has the form of a cylinder and which has an opening on the right side from which the water sprays out. First, let's visualize the situation. Point 1 is inside the tube and point 2 is in the opening. At point 1, the diameter D1 is 10 centimeters and the pressure is 2.85 bar. At point 2, the diameter of the opening D2 is 4 centimeters. The water jet leaves with a velocity of 15 meters per second. Next, we will construct a mass balance over point 1 and 2. It's a steady state, so the accumulation term is 0. There is no chemical reaction, so the production term is 0. This leaves us with the mass flow in being equal to the mass flow out. The mass flow can be rewritten in terms of the volumetric flow, but the density can be crossed out as it doesn't change. And this in turn can be replaced by the velocity times the area. Isolating V1 and filling in the area of the cross section, which is a circle, so pi over 4 times the diameter square. Now filling in all the numbers, 50 meters per second times the square of 4 centimeters over 10 centimeters. This leaves us with 2.4 meters per second. Now let's write up an energy balance in order to find the pressure drop between point 1 and 2. To start off, let's think of what assumptions we can make. First of all, it's a steady state. Second, the energy dissipation is 0. And no work is being applied to the system. So the work term is also 0. With these assumptions, we can apply Bernoulli's law. The hose is horizontal, so there's no height difference between point 1 and 2. Considering this leaves us with the pressure drop being equal to half the density multiplied by the difference of the squares of the velocities. Filling in all the numbers, we find 1.096 bar. In order to find the force that the flange exercises on the water, we will set up a momentum balance in the x direction. This has the form of the derivative of the momentum, so mv, with respect to time, equals the mass flow times the velocity at the entrance minus the mass flow times the velocity at the exit, plus the sum of all forces. It's a steady state, so the accumulation term is 0. And we can find the mass flow by multiplying the volumetric flow with the density. And we can find the volumetric flow by multiplying the velocity with the area. Note that here we used values for point 1 in order to find the volumetric flow. But we find the same value if we use the values for point 2, hence the first part of the exercise. We find a value of 0.018 cubic meters per second for the volumetric flow rate. The forces that play a role here are the pressure that the flow applies on the cross-sectional area and the force that the opening, the flange, exercises on the water. So the sum of all forces is the pressure times the area at point 1 minus the pressure times the area at point 2 plus the force that the flange exerts on the water in the x direction. Now we will first calculate the pressure at the point 2, since we've only calculated the pressure drop between point 1 and 2, but not the actual pressure at point 2. So when calculating this, we find 0.9825 bar. And now we will isolate the force that the flange applies on the water from the expression we found earlier. And then we fill in all the numbers. Remember to check the units. We find minus 1,286 Newton. Thanks for watching the answer video and good luck with the rest of the exercises.